Hello maths fans, Dr Tom Crawford here at the University of Oxford with another video in the Oxford Calculus series. Today we're going to be deriving the heat equation. This is one of the first PDEs you will see as a maths undergrad, as it can be solved by looking for a separable solution and using the technique of Fourier series. Both of these topics will be covered in later videos. Our starting point is going to be to derive the equation itself. In one dimension, it looks like this. We have the time derivative of the temperature, where this curly d represents a partial derivative. And this is going to be equal to a constant kappa, which will depend on the material properties where the heat is being conducted. And that is multiplied by the second spatial derivative of the temperature. And here we're going to use x, as this is our variable in one dimensions. To get a feel for how the heat equation works, I recommend heading over to the Maple Learn worksheet linked in the description to play around with the solutions. There are some handy sliders that allow you to see how the solution changes for different initial energies and different material properties. And hopefully you'll agree that the solutions do a good job of representing how we might expect heat to move through a conducting material. To derive the equation in 1D, we start by imagining a long rod along which the heat is flowing. And I'm going to draw this as a very long and thin cylinder, and this is going to have some fixed cross-sectional area which is going to be equal to A. Now we're studying this in one dimensions, so I'm going to add my x-axis through my very long, thin cylindrical rod, and the direction of travel of the heat is going to be from the left to the right. Let's look at 2 points. Let's say the left-hand side here is x equals A, and then for small h, we will consider another point along the rod, which can be x is A plus this small amount h, and ultimately what we're going to do is let h tend to 0, taking that limit, and hopefully get an equation for the temperature at A, and then use the fact that it was a general point, and so therefore the equation we derive has to in fact be true for the whole rod. Now, we want to consider how the internal energy of our rod is changing within this small segment. And at this point, we need to actually borrow some knowledge from our physics friends. So our friends over at physics can tell us that the internal energy for a rod in one dimension of length h from A to A plus h is going to be equal to the cross-sectional area A, which is constant, multiplied by the integral from A to A plus h of 3 things. So we have rho, where rho is the density of our material. So I'll add this up here. Rho is the density. And a second property of our rod or our conductive material that we're going to need is the specific heat capacity represented by C. So we'll also say it has C is the specific heat capacity. So the formula says the internal energy is rho C times the temperature T, which remember is what we're interested in, and then we integrate this with respect to x. So this is the internal energy of this segment of our rod where there will be heat flowing through this rod. Now we want to know how this is changing. So if we want to know the rate of change of the internal energy, then what that means is to take a time derivative of the internal energy. So if I slightly modify this and say we want the time rate of change of the internal energy, then that's in fact now going to be equal to d by dt of the internal energy. Now looking at the diagram, I've said a few times that heat is going to be flowing along this rod. The heat is being conducted, it's moving. Now, what we're going to suppose is that there is a heat flux in on this side. So heat in, and it's coming in at some rate Q, and this is evaluated at A and is also a function of time. And then there's going to be heat leaving, because we've said the heat is flowing from the left to the right. So heat is leaving, heat out at the rate Q, but now it's evaluated at a different value of x, because we want the value of the heat flux at A plus H time T. So we're assuming there is a function Q which describes the heat flux, and we will talk more about that shortly, but for now we'll just call it some general unknown function Q representing the heat flux. It's evaluated at A, and it's coming in from the left-hand side, and it's evaluated at A plus H, it's going out on the right-hand side. So the time rate of change of the internal energy, the change in the energy within this section of our rod, has to be equal to the energy coming in, which is positive, the energy is increasing, so it's plus Q at AT, and then we're losing energy from the flux out on the other side. And we also multiply both of these by the constant area A. So we have a total flux Q coming through the area A, in on the left, and then out on the right. So it's minus A times Q, A plus H, T. So now we've begun to formulate a mathematical expression for the change in energy of this piece of our one-dimensional rod. So far, we have that the time rate of change of the internal energy of our rod is equal to the heat flux in minus the heat flux out. Now, some of you might be thinking, well, could heat not escape through the rod itself? Could the heat be lost to the surroundings? And this, of course, is true. This could indeed happen. Now, in this particular derivation, we're actually assuming that the long, thin rod is insulated. So what that means here is that heat cannot be lost through the boundary of the cylinder itself. Heat can only flow along the cylinder and potentially be lost through either end, depending on the boundary conditions. But in terms of our derivation, the only way that we're assuming our internal energy can change is by flux in on the left and flux out on the right. Now the constant A, this cross-sectional area, is of course appearing on both sides of the equation. It is a constant value because we're assuming a constant cross-section of our cylinder, our rod. So we can of course just cancel this on both sides. And one other simplification we can make at this stage is to actually take this time derivative inside the integral. Now, some of you may know how to do this. Don't worry if you don't. The key thing is a law or a rule called Leibniz integral rule, which I'll write here for you. So Leibniz integral rule. And what this tells you is basically how to differentiate an integral. Now, in this situation, we have a very simple setup because our integration limits are constant. So when we have constant integration limits, they don't depend on time, so this derivative does not interact with the limits of our integral. What happens is the full derivative outside of the integral, according to Leibniz rule, this becomes a partial time derivative inside the integral. So we take the partial time derivative of this function, the integrand. Now, rho is the density, which is constant. C is the specific heat capacity, which is also constant. So all that happens here is we have to take a partial time derivative of the temperature. Now I'm just going to write this as a subscript T, which is shorthand notation for the time derivative with the curly D that I've written at the top of the board. So this is where our time derivative comes from, and we can now actually rub off the d by dt because we've taken it inside and simplified the derivative on the left-hand side of our equation. Now if we look at the right-hand side of this expression, we have a function, q, of x and t. It's a function of position and time. And we have it at a point A and a point A plus h, and we're taking the difference between them. Now, we've seen something like this before. If you've studied any form of calculus or anything to do with differentiation, in particular taking derivatives from first principles, this hopefully is reminding you of that kind of topic. So if I in fact take a minus outside, which then makes this one a minus and this one a plus, then what I've got inside the square bracket is a function at a plus h minus a function at a. Now, I said at the beginning, what we want to do is actually take the limit as h tends to 0, because then that will give us the governing equation for the temperature at a point A. A was an arbitrary point, so therefore the equation we're going to derive will in fact be true for any point along the rod, i.e. for all x. So that's what we want to do. We want to take the limit as h goes to 0. So this looks very similar to a derivative. And in a derivative, you take the limit as h goes to 0. So what we can do here is, using this similarity that we've spotted, we can in fact say, well, what if we divide this by h, and then also let's now take, let's now take the limit as h goes to 0. Because this expression on the right-hand side of our equation now exactly looks like a derivative. Now, because we have a function of two variables, q is a function of space and time, this is actually a partial derivative. And it's the exact definition of a partial derivative with respect to x evaluated at the point A. And you can see why, because t isn't changing. So we have our function q, which depends on space and time. And what we're doing here is saying fix time, hold time constant, make a small change in the x value, so go from a to a plus h, very small change in x, and then divide by that change and look at the limit as the change tends to 0. So this is exactly how you define an x partial derivative. And instead of doing it at some general point x, we are evaluating it at the point x equals a. So this whole expression, once we take the limit, is actually just going to give us minus dq by dx, our partial derivative with the curly d, evaluated at x equals a. Now, of course, we need to do the same to the left-hand side of our equation. Namely, we need to divide by h, so I will put a 1 over h here, and then take the limit, which I'll write in here, as h tends to 0. So the equation now remains valid, because remember, we did a division by h, and then took the limit and said, well, that's exactly the definition of a partial derivative at x equals a. So if I do the same to the left-hand side, then the total equation remains valid. I've done the same to both sides. Now, this thing on the left, it's interesting, because what's happening is, again, we have 1 over h, and we want h to go to 0. So our denominator is definitely going to 0, just like we had over here. But we kind of made sense of that on the right-hand side with our derivative because the numerator also went to 0. As h tends to 0, this goes to q at at, and then you subtract the same thing. So the derivative here is making sense of 0 divided by 0 through this formal limiting process. So if we try and do something similar over here, because the numerator on this left-hand side is also actually going to 0, because we have the integral from a to a plus h. So we're integrating over a segment, a line interval of width h. So as we let h tend to 0, we're actually then integrating from a to the point a. So the width of our integral is tending to 0. And if you integrate anything over a width of 0, you get 0. So again, regardless of what's inside the integral, the two limits are tending to each other as h goes to 0. So again, we've got 0 divided by 0. Now, just like we dealt with it on the right-hand side by rewriting this as a derivative, we need to think about what's the sensible way, or can we somehow evaluate this limiting process of 0 over 0 in this context. Now, what we've got is a function which we're integrating, and we're integrating it with respect to x, so the direction in which h is being added, from a to a plus h. So if you think of integration and differentiation as opposites of one another, and given that this process turned into a derivative, you can kind of think of this process, and of course you can make this rigorous, but I'm trying to just give you some intuition. You can just think of this process of doing a derivative. So you're dividing by h, letting h tend to 0, you've got like 0 over 0, so it's kind of like a derivative like we had on the right-hand side. So if you kind of take a derivative of an integral, again, they're going to cancel out because they're opposites of each other. That's what the fundamental theorem of calculus, in fact, says. So with that in mind, we can think of saying, well, taking the limit as h goes to 0 and dividing by h, when the integral is of width h, that's actually the same as cancelling out the integral. So we're just going to get back whatever's inside the integral. But we're kind of getting this function evaluated at the single point which the two limits tend to. So again, you can do this formally and you can rigorously calculate this limit. You can also actually use Liebniz Rule to help figure out exactly what's happening here. But hopefully you'll believe me and it follows a sensible way of defining what does this limit mean, to say this sort of cancels out with the integral, and what we're going to get is just rho c. We're going to get the time derivative, which I can write out fully, and that's going to be evaluated at x equals a. So now we have an expression relating the time derivative of the temperature with the spatial derivative of the heat flux, Q. You'll see at the top there isn't a Q in our equation, so we still need to do something about this Q, which is going to be our next goal. But for now, we can see we have a relationship between them. Both sides of the equation are true at the point x equals a. Remember, a was an arbitrary point along our rod. Therefore, this must be true at any point a. Therefore, this is in fact true at all values x. So we can in fact rub this off and say the behavior of our heat flux and our temperature, they are related by this equation. Rho c dt by dt is equal to minus dq by dx. The final step in our calculation comes from calculating what the heat flux Q actually is and how it's related to our temperature T. And once again, our friends in physics are here to help. The law that we need is called Fourier's law, because this was discovered by Joseph Fourier, a French mathematician, whilst he was looking at the heat equation. And in fact, this was the motivation behind Fourier series, which are generally what you would use to solve the heat equation. But we don't need those here, we just need his law. Now, he was studying the flow of heat, and the way that it behaves, the way that this flux relates to the temperature, actually fits perfectly with our everyday experiences of heat transfer. So if you have a hot object, it will cool down because heat flows from a hot area to a cool area. So if we were to have a plot of the temperature, which let's say looks something like this. So here the temperature is high, and over here the temperature is cool. Then our everyday experiences tell us the heat will move in this direction. So heat moves against the temperature gradient because the gradient here is positive. This is a function with a positive gradient, a positive slope, and the direction of flow of the heat is against that gradient. And that's exactly what Fourier's law says. So Fourier's law will tell us that the heat flux Q is equal to minus, and then we've got the gradient, which is dt by dx, and there's also going to be a constant K, and this constant K is called the thermal conductivity, because this tells you the rate at which your heat flows, and that's going to be dependent on how conductive your material is. If we now take Fourier's law and substitute for Q into our expression, we're going to get a minus gives us a plus, so we have a K, and then we have a second derivative of T, where importantly K isn't affected by the derivative because K is a constant. And if we now take the row C up here and divide on this side, we can rewrite to say the time derivative of the temperature is equal to the thermal conductivity of our material divided by the density of our material multiplied by the specific heat capacity multiplied by two spatial derivatives of the temperature. So finally, we just define these constants to be kappa, which is called the thermal diffusivity. And now we have the exact same equation, which we've derived from physical principles, as the original heat equation in 1 dimensions that I wrote at the top of the board at the beginning of the video. This derivation was for a 1-dimensional rod, but this generalizes to 2 dimensions and 3 dimensions by adding in the appropriate spatial derivatives. So for example, if we had a 2D situation, we add in d2t by dy squared, and if we wanted to go into 3 dimensions, you guessed it, you get a d2t by dz squared term. And in fact, we can express the whole equation very succinctly using the Laplacian operator. Now, don't worry if you haven't seen this, it just basically tells you to take 2 derivatives in each of your spatial derivatives. So in this context, you would write the heat equation as the time derivative equals kappa times the Laplacian of the temperature. So you may also see the heat equation in this form, where this operator is the Laplacian, and in 1D, 2D, and 3D, it looks like the purple expression in 1D. In 2D, you have the x and the y, and then you get the z term if you're going to 3 dimensions. Now that we've derived the heat equation, it's time for you to put it to use. Head over to the MapleLearn worksheet linked in the video description for lots of practice questions related to the content that we've discussed in the video. And as I mentioned earlier, Do make use of the interactive plots to really get a feel for the equation and how the solutions behave. Thank you everyone for watching. Please do remember to subscribe if you've enjoyed the video, and I'll see you all soon. Take care.